Hi everyone, my name is Oluwaseun Oyekola from Cape Peninsula University of Technology in Cape Town, South Africa. I'll be presenting a project titled Optimization of Densification Conditions for Carbonized Corn Stover Briquettes. Maize is a staple food in South Africa, and South Africa is also the largest producer of this crop in Africa. However, with increasing population and food demand, the problem of this agricultural residue management is becoming serious, owing to the fact that corn stover can be very bulky and difficult to handle. Its storage and transportation is also a challenge. Corn stover refers to stalks, leaves, and cobs that remain in fields after the corn is harvested. Based on the fact that South Africa is the largest producer of this maize in in Africa, a large amount of residues are formed. 9 to 16 million tons per year of corn residues are formed, and only 70% is used for soil conditioning and for animal feeds. So owing to this, quite a huge amount still remains that needs to be handled. However, owing to the fact that this biomass has 70% cellulose and hemicellulose, it is a good potential for as energy source. South Africa is currently facing a shortage of electricity. At the moment, there have been blackouts occurring regularly, and also the country depends solely on coal, which as we all know is finite, and its usage is associated with greenhouse gases emission. Hence, there is a need to look for alternative sources. 80% of households, while 80% of households have access to electricity in South Africa, up to 3.4 million households still have no access to electricity, and most of these households are located in the rural areas where they have to depend on firewood. Hence, another challenge comes to the fore, which is pollution and associated health problems. While this might be gloomy, might sound like a gloomy outlook, there is however potential in valorizing the corn stover waste. The three major routes of exploiting the energy potential in crop residues are direct combustion, which is co-firing with coal. However, this is associated with pollution. Another route will be biochemical processes such as anaerobic digestion, biodiesel production, or ethanol production. However, these processes are costly. So the one that is focused on in this study is a thermochemical process. Of the different thermochemical processes available, we are looking at slow pyrolysis because it produces a huge amount. 35% of the product is biochar, which serves as a starting material for briquettes. Briquettes has been referred to as an eco-friendly solid fuel because it's smokeless, it has slow ash, it's smokeless when it is combusted, or when it's used as energy source. It has low ash content, low to no free little to no sulfur content, and it also has reduced greenhouse gas emissions, and it's also characterized by high calorific value. And as shown in the pictures in this slide, you can see that it's associated with uniform combustion. Those are briquettes obtained in the current study. The aim and objectives of this study are to produce the eco-friendly solid fuel from corn stover that is taken through a slow pyrolysis process to produce biochar, and the biochar is subsequently densified into briquettes. the process that the approach that has been adopted is as follows. The corn stover is collected from a farm, and this is taken through series of processes such as size reduction, milling, and then this is pyrolyzed. While the pyrolysis process produces bio-oil and biogas, which can be used as other sources of energy actually that can be used to power the current process. Biochar is, however, our emphasis in this particular research. This biochar is then taken through mixing with a binder. In this particular case, the binder adopted is cornstarch, which was obtained from a sugar producing company. In essence, all the materials used for this process are waste. This is then taken through, after mixing, this is then taken through briquetting or densification. The briquette is then characterized and stored. In order to achieve these objectives, the optimization objective, what we adopted was response surface methodology, and the process variables that were adopted based on literature, that were focused on based on literature, are drying temperature, compressive pressure, and binder concentration. These have been coded as ABC respectively. The response factors investigated were higher heating value (HHV), durability or the mechanical strength of the briquette, and density. The results obtained are presented as follows. For the HHV optimization, it was found that the only factor that has significant effect was the binder concentration. However, if you look at the quadratic equation that has been provided, you see there that the coefficient is negative, meaning that with increasing binder concentration, the HHV will reduce. This can be attributed to the fact that the cornstarch that has been used has a lower HHV. While it has a lower HHV, it can also be said that its impact in reducing the HHV is quite minimal, is not so significant. However, it's not so significant on a larger scale, but when compared to the other factors, we say that it's only the significant factor, and the HHV range that were obtained were 25 to 29 megajoules per kg. From you could see that this is a huge increase from 16.8 megajoules per kg of the original biomass. For the compressive strength optimization, two factors were found to be significant, and these were the compression pressure and the binder concentration. These two have positive impact on the compressive strength, and this can be attributed to the fact that these two close up the spaces within the particles of the biochar. So all pores and voids are closed and are filled by the binder, resulting in a stable and solid briquette. Further, the intermolecular bond created when the pressure and binder concentration is increased. This also can be attributed when it comes to the density optimization. So compression pressure and binder concentration also have positive impact owing to the same reasons that were explained earlier on that were explained earlier on for the compressive strength. For the durability optimization, the three factors that were investigated were shown to be significant. While compression pressure and binder concentration have positive effect, the drying temperature has negative impact. And this can be attributed to the fact that when the temperature is increased, there is a rapid release of moisture leading to cracks formation in the briquettes. Hence, the durability of the briquette is adversely affected. While this is adversely affected, the durability range obtained in this study is still very high, which is 97, between 97 and 100%. The optimum conditions predicted using the RSM were then verified by carrying out experiments under these conditions. The briquettes obtained were then characterized. As shown in the table, we can see that these characteristics, the HHV, the strength, density, and durability, fall within the 95% prediction interval. Hence, the models that were proposed, the models that were gotten from the RSM were found to be reliable. So in conclusion, we can say that the briquettes that were produced from corn stover have good qualities, including the fact that the HHV is comparable to that of bituminous South African coal. Hence, it's a potential cleaner substitute for coal. And also, apart from the substitute, it can also be used to supplement the finite coal. Thank you for your attention. I would also like to appreciate I would like to appreciate NRF South Africa for their funding, and also Cape Peninsula University of Technology for the support. I'll be taking any question regarding the presentation, and these are some of the references that have been cited in